Hi, in this tutorial I'm gonna talk about the naive Bayes classifier. But before talking about that, I need to review a couple of stuff to see if we are in the same level. So just some review. Okay, we know that the independent events are, let me just write it down. Okay, so A and B are two independent events if the joint probability of them is equal to probability of multiplication. And well, an example gonna be A observing 3 on a dice and B gonna be having a head on a coin. And it's pretty intuitive. And if I write down the Bayes rule, probability of A given B is equal to joint probability over B, which if I use the first line, it just only give me probability of A. And it of course it's same for probability of B given A, so give me probability of B, and also probability of A and B complement are independent. Okay, now we go to conditional okay, if two events A and B are conditionally independent of C, then the joint probability of them gonna be probability of A given C multiplied by probability of B given C. And please note that A and B are conditionally independent of C. So A and B may not be independent, but in the presence of event C. You can just toying around with formula and massage a little bit to get this A okay. How did I get there? It's pretty simple. Just probability of A given B and C. Use a Bayes rule, A, B, C over B and C. Now if I took these two as one variable called D and then use a Bayes rule, then I can write it down like probability of A and B given C multiplied by probability of C over probability of B and C. And here I use this line. So probability of A given C multiplied by probability of B given C over probability of B given C, which is probability of A given C. Okay. And the other thing I like to tell you that A and B are conditional independent of C. That means A. And this doesn't necessarily mean, not necessarily mean that this is true. So not necessarily. And also if A and B are independent of each other, it doesn't necessarily mean, this notation doesn't necessarily mean that A and B are independent of C. So this should be taken into account. Just keep in your mind that this is not always true. You have to be careful. Okay, now we're going to Bayes classifier. Okay, what is Bayes classifier? So you have some classes, and you have a set of feature f1, f2, fn. For instance, you install some sensors which could sense the foot size and height of a person and weight of a person. And then you have some classes like male and female. Okay, and you do some observation for instance, I don't know, 100 observation, and you compute and you measure the foot size, height, and the weight, and you can see if it's a male or female. And then you have you install your sensor somewhere, and then you have some measure some data. You have some incoming data, and you like to know the class, if this is most likely a man or women. So probability of being male or female given this set of features fn. I use a Bayes rule here, is equal to probability of f1, f2, fn given multiplied by probability of c or probability of f1, f2, fn. Okay, so this is called posterior equals to prior multiplied by likelihood over evidence. Okay, a little bit about this. So probability of C, probability of classes, in our case, since we don't know any extra information, it's 1/2 for each class. So there's a 50% chance of male, 15% chance of being female. The evidence term here is a normalizer, because here we want to have a valid probability number. So this evidence is just sum or integral over all this value in the denominator. So actually we don't compute it directly, we compute it indirectly. And the likelihood is the probability of this feature given class. Okay, if you remember from the previous slide, for two variables which are conditionally independent of C, you could just write it as a multiplication for. And here we have an assumption that these features are independent of each other given C. And that's why it's called naive Bayes classifier, because for instance, in our case, we know that the there is some connection between foot size and height, for instance, but we model it with this assumption that these are conditionally independent of each other. So I can write it down in the form of probability of f1 given C multiplied by a probability of f2 given C till probability of fn given C multiplied by a probability of class over the probability of f1, f2, and fn. And as I said, we don't compute this. Just grab my blue marker. Okay. We usually, for this guy, we usually use the uniform distribution over all the classes. If you have 10 classes, then we give them 1 over 10, or if we have some assumption, we can put it here. This guy, I told you, you don't compute it directly. And what about this guy? How do we compute each one of these terms? Okay, so in our case that we have foot size, height, and weight, we compute the mean and the covariance or variance, and then we assume that they are coming from some normal distribution, because the foot size, the height, the weight, these are always in the form of normal distribution. The foot size have some normal distribution peaks, and we compute the mean and variance, and we get something like this. For instance, for let's say these are the weights for class male. Okay, and we know that this is a PDF function, and PDF function, a point over a PDF function doesn't mean anything, or always integral over a given range is the probability of that feature to be between A and B. So that's always something that makes sense. Otherwise, a single point doesn't make any sense, because the probability of exactly one specific value is 0, because the we always have to compute this integral, and then you have a line with the length of a 0. It's and with width of a 0. It's probability is 0. Okay, but we use this value here because, as I said, we have to compute this integral, and to compute the integral we can say, okay, the height, I mean this length multiple by this length, delta x, and delta x is a very small number, and the limits goes to 0. And we have this delta x both in a numerator and denominator. As I said, the way that we calculate this is just computing this for all the value in the denominator, and then sum it up, or use a sigma or integral, depending on if we're in discrete or continuous space. And these two delta x on the numerator and denominator gonna cancel out each other. So actually we use the value on the PDF function. So I have done everything for these naive Bayes classifier on a Python file, and I have put all the steps there, all the curves, and how do we compute all this value, and you can have a look on that. I will put the link in the comments, in the description. And also I use the scientific learn package from the Python to compute the classification results, and you can compare these two. And if I just want to write it down, it's gonna be something like this. The stereo of being male is equal to probability of male, which is 50%, multiplied by a probability of height given male, multiplied by probability of weight being male, multiplied by probability of foot size being male over evidence. And as I said, for this guy, and this guy, we fitted our data to some Gaussian curves, and for our incoming data, for instance, the height is, I don't know, 1.8 meter. So maybe it falls somewhere around here. 1 point. We read the value. The weight might be something like, I don't know, 70 kilogram. So this is the, here less than the average. We read this value, and the foot size, the person might have the shoe size of, I don't know, 46, which is too big, and he probably falls in this side of the curve. So we read all this value, we put them there, and then this guy is 1/2, and then we compute the posterior of male and then female, and then compare. We pick the one which has the highest value. Okay, thank you for your attention, and bye.